All right, thanks everyone for coming. Be sure to silence your phones. So it looks like a lot of you here are old enough to have been playing DOS games, so that's pretty good. I don't have to over-explain things. How many of you are programmers? Wow! I was trying to, I do get technical, so it's nice that most of you won't be lost. So for those unfamiliar, I'll just show a quick trailer of Retro City Rampage 486, which is the port for old PCs. So it was pretty amazing to do this and be able to release it on a single floppy disk in a box. And honestly, the warm and fuzzies in me got most triggered by this little thing in the corner. Doing this in Photoshop was just so nice, putting the little system requirements in there. The funny thing about DOS is that it's a bit different because a lot of people are developing now for retro platforms and stuff. And I was no exception. I was developing on NES stuff. I started learning it way after the fact, teaching myself how to do it and tinkering away. But the funny thing is about DOS is that it's actually something I was programming on in the 90s. So it's totally different. It's not just like, oh, I wonder what it was like. I remember what it was like. And so it was neat because it was a bit like riding a bicycle, and a lot of things came back. I'm going to preface this talk by just explaining what exactly the goal was here. And so in a perfect world, I would have optimized this game so heavy that it would be running on a 286 and 16-bit mode. But the reality is that it wasn't originally written to be running on a 486 or a 386 or whatever. And so I did a lot of things in there that aren't necessarily, like, for example, using floating point and stuff. And so if I were to go back in time and be writing this game from the ground up, I could have written it to run on a 286 and not use an extender and all of that stuff. But really, when you're thinking about a project like this, you've got to figure out, well, do I want to spend a year on it, or do I want to spend a month and a half? And kind of time is valuable. So I figured 486 was pretty cool. Not as cool as a 286, but kind of still cool. So my goals here were, number one, to increase performance in the game's code so that it could run on a 486. And my second goal was to reduce the memory usage so that it would run in under 4 megs of RAM. The reason I chose 4 megs specifically was because that was a reasonable amount for a 486 of the era. And finally, I needed to reduce the actual file storage so that it would fit on a single floppy disk. So since most of you are programmers, you're familiar with this type of thing, trying to decide whether you want to have small code or fast code. So is it going to inline a whole bunch so it's a bit faster, or is it just going to kind of keep it tight? In this case, however, though, I did have my 3 points that I had to weigh, and often I had to choose just one. So I could choose code speed or RAM usage or disk storage, not necessarily all three. So one example here is drawing the graphics. The background tiles are 2 bits per pixel. So that means I can store 4 pixels in each byte. But since I'm rendering in 8 bits per pixel, if I store it in 8 bits per pixel, I'm wasting a lot of bytes, but I can super easily just memcopy it. But because, I want to use a quarter of the memory, I did decide to store it in 4 bits per pixel, or 2 bits per pixel. So as a result, I did have to decode it a bit, and so that's a CPU killer, but in this case, RAM was more important. So of course now, we're all used to nice SDKs that are filled with readable documentation and sample code and all the awesome stuff that we have. Unfortunately, most of the best DOS resources and machines are now here. In fact, I didn't realize it until I looked for it, but I had gotten rid of all of my old PCs and I had to find one off eBay. And They're actually pretty expensive now. Who would have thought they'd be vintage? I mean, all of our PCs are always backwards compatible, so we never really gave the love to an old PC that we would have maybe to keeping our old Commodore 64 or something. And so it's actually pretty hard to come by cheap 286s, 386s, and so on. And the same can be said for books. So unfortunately, like most of you, I'm sure, I got rid of most of my DOS programming books, figuring they were long obsolete and I'd never used them. Luckily, I did happen to save one. I don't know how, but I did, and it was useful, and I was actually able to use it for this development. But I really wish I had the rest, because the fact is that most of the really good DOS information is now stuck on books somewhere, hopefully not all recycled. When you're searching online, sometimes the only really resource you can find are forum posts. And often they're wrong, and so you have to take them with a grain of salt, and you can't just take them as fact, such as this one. If you were to use this code to test if a coprocessor was present, you would be detecting a lot of incorrect setups. So you would think that there's no coprocessor when there actually is on many machines. The internet kind of hit the mainstream after DOS had faded. So you're not going to find a lot of enthusiast websites that talk about programming DOS and have tutorials and sample code and so on. So while we do have awesome things for most SDKs now, like MSDN for Windows programming, we don't really have that for DOS. So the API that we would be used to, for example, for any system, show cursor false to hide the mouse cursor. On DOS, it would be more something like this, moveax2 int33h. Of course, truth be told, you would end up just wrapping it like this, and you would be coding in a nice API yourself anyways. But there was no real off-the-shelf DOS SDK the way we consider nice APIs and SDKs today. Certain compilers did have their own, like Borland had BGI for graphics, but there was no standardized DOS API and SDK. So the best we have here generally is the interrupt list. So I'm sure a lot of you remember Ralph Brown's interrupt list, which was kind of the golden book. But you can see the difference here versus Windows documentation and the DOS documentation. You would end up memorizing all the interrupts that you're going to use, the ports you're going to use. So int10h is video, 33h is mouse. But if you didn't know that, you would end up looking through these categories, mouse and pointing device. And then you would find this, which is kind of overwhelming. And of course, the reason is, you're like, well, what do I use? How do I use the mouse? Well, it's because there was no standardization back then. And everything just had their own random driver, their own random interrupts. But you would eventually find exactly what you're looking for. And in this case, to show and hide the mouse cursor, it's AX1 and AX2. So having the documentation and the API and all that stuff good to go, the next thing that we need is a compiler. And so I did most of my C++ programming on Borland C++, so that's the one that's kind of in my heart here. But I had to be equal opportunist and, look at all the compilers available. So ideally, I wanted to be able to use my main PC. So I didn't want to have to boot up my old Pentium 1 and do all of my development on that. I also wanted to have a native IDE if possible. So I didn't want to have to boot up DOSBox or a VM and run some Windows 3.1 IDE through that. I also wanted to be able to cross-compile from Windows. So ideally, I didn't want to have to run makefiles through DOSBox. And I also didn't want to do any major code changes just to get it to compile, let alone develop for it. Because a lot of compilers aren't necessarily going to support the latest and greatest C and C++. So compatibility is surprisingly an issue, because even Visual Studio 2003 already had compatibility issues 4 years later when they released Vista. And so Borland Turbo C++ 2006 and Visual Studio 2003 don't work properly or even install properly on current versions of Windows, no matter how you tweak and tune the compatibility settings. So when you're rewinding the clock a bit further, you could be faced with even more headaches. One thing that I encountered, of course, was the fact that they didn't support all the C++ features. They just weren't around yet. So Borland C++ didn't support templates. And although I don't use them to excess, I only use them reasonably where they make sense. And I could have modified my code to not use them. I didn't want to do that if I didn't have to. Another big thing were the 8.3 file names. So back then, file names were 8 characters with a 3-character extension. And of course, I could write some sort of script that renames the files and updates the includes, but if I didn't have to, I didn't want to. But then I found OpenWhatCom. And so does anyone know about OpenWhatCom? Okay, so it's amazing. It's open source, it's free, and it runs natively under current versions of Windows perfectly. It supports all the C++ you need, and it cross-compiles for DOS, Windows 3.1, Windows 95, and current Windows, OS 2, Linux, and a whole bunch of other stuff. So it's amazing, and it totally saved the day. And not only that, but it also includes native IDEs and debuggers for Windows 3.1 and for DOS. So if I really do need to debug something right there on Windows 3.1 or DOS, I can. I do have one little trick up my sleeve, though. And that's the fact that even though I'm porting to DOS, a lot of the stuff that I'm doing isn't really DOS specific. I'm crunching the game down to use a small amount of memory as possible. I'm reworking it to work in 320 by 200, 256 colors, and so on. So, with everything I do, I always keep a native Windows version. And this allows me to use the IDE and debugger that I'm most comfortable with, that I love to use. And the 99% of the code that isn't really DOS specific, it's not PC speaker stuff, it's not DOS memory allocation, it's not timer interrupts, all of that stuff that's not that can just be done in Windows. I actually do this on all my platforms too. So whether it's 3DS, I have a native Windows version that does the 2 screens with the bottom clickable with the mouse to simulate touch, or whether it's iPhone where I have the touch screen as well usable with the mouse. This all just saves my time so much. I don't have to worry about uploading to the dev kit. I can use the debugger I want, and iteration is just super fast. So the little upfront time it takes to do 2 video renderers and 2 sound managers and so on is totally worthwhile. So that stuff out of the way, now we can actually get to real DOS programming. And so the way generally DOS would work for drawing graphics on the screen was to use these bit planes. So you would think, oh, it should be straightforward. If I'm doing a 16-color image on screen, that's 4 bits per pixel. So I just draw the pixels linearly, 2 per byte, and I'm done. Unfortunately, that's not how it was. Instead, a lot of these DOS things, a pattern you'll see, is that the hardware was super primitive, and a lot of stuff that should have been done in hardware was done in your own code, which really hogged the CPU needlessly. And so nowadays, we kind of don't have APIs and stuff like that. But back then, that's how DOS was. So if you wanted to draw 1 pixel on the screen, you would actually have to draw 4 pixels in 1 bit each. But I'm sure everyone who did DOS programming knows about mode 13H. And so this came along and is amazing. It gives you a single address you write to that's effectively a byte array. And you can just write your 320 by 200 bytes. And as soon as you write it, it's on screen. And you've got your 256 color graphics, no time flat. It does have pros and cons, though. So of course, the pros are it's super simple, 1 byte per pixel. And it's fast. You could just memcopy your pixels and you're done. Unfortunately, it can't double buffer. So you do have to worry about screen tearing and making sure that you're updating it right when the Vblank happens. And secondly, it wastes a lot of video memory. And this is the trade-off, is that mode 13H does a lot of work for you to make your life easy. But even if you have a 256K video card, for example, and 320 by 200 pixels is only 64K, you're not getting that extra memory. And so you just get 1 page. There was mode X and mode Y, as I'm sure some of you coded back in the day, which allows you to do your 256 by even 240, or your 320 by 240, which would give you square pixels, and you can have page flipping and all the awesome stuff you want. But again, that becomes more complicated, and it's a bit more CPU to deal with that. So I just decided to call it a day and stick with my good old mode 13H. And so since you're all familiar with DOS, you're all familiar with palettes, and they couldn't be easier to write. The 256 color screen is indexed color, which means your actual RGB values are stored in a palette, and the screen is just indexes, and those indexes reference the palette. And to write that, it's simply outputting the index to one port and the RGB values to another. The other thing we want to do is we want to make sure that we're in Vblank so that we can update the game, the frame without tearing. Things do get a bit more complicated, though, if your game doesn't necessarily always run under 16 milliseconds on every single IBM PC ever, in which case you want to do some frame timing to make sure. And that's where things get a bit counterintuitive. So if you were to just use the standard C clock, you would be pretty surprised because, oh, maybe DOS only has 1 millisecond of precision. Well, not even, not outside the box. It uses the PIT on IRQ0, which only ticks every 55 milliseconds by default. And so if your game's running at 60 frames a second, or it's trying to, it's not even ticking every 3 frames. So it's completely useless the way it is. But you know what PIT stands for is programmable, and so you can actually change it. So the IRQ at interrupt vector 8 can be changed, but by default, it holds a value that starts at 0. It ticks and counts that up to 65535, the top value, and then it rolls back to its start value 0 and kicks off your interrupt. And that's what's ticking our clock. So when it ticks from 0 to 65535, that takes 55 milliseconds. But we can change that value, so if we put it halfway in between, to 32768, it only takes 27.5 milliseconds. Split it one more time, we're down to 13 milliseconds, and so on. So you can choose whatever value you want, but there is a caveat, because there were other things using that interrupt that were expecting to be kicked off at 55 millisecond intervals. So what we need to do is we need to keep track of those. So we need to grab the old callback that was being called, save it. We can modify our interrupt however we want, but we have to try and make sure that we're kicking that off at its expected 55 millisecond intervals, which means that we want to, even though we can technically choose any value between 0 and 65535, you do want to choose an even slice. So if you slice it into 8 even pieces, every 8 times it runs, you can kick off the old interrupts. So we've got our frame timing and we've got video drawing. The next thing that we're going to do is get sound going. I chose to do the PC speaker. I know that disappointed some of you who wanted ad-lib or Sound Blaster, but there are some pretty big advantages to this. Number one, it saves a lot of memory. Number two, it's in every single PC. And number three, it just gives me warm and fuzzy feelings. So. So the sound for Retro City Rampage was originally composed in Mod Plug Tracker, using 5 channels to mimic the NES. So we had a square wave, a triangle wave, a noise, and a DPCM. But on DOS, we just had this single channel beeper. So what I did was kind of the quick and dirty way. I went through every single of the sound effects, all 215 of them, and by hand recomposed them to be a single channel beeper sound effect. Rather than creating some sort of big, nice, robust PC speaker editor that was what you hear is what you get, I just used Mod Plug, made it a single channel, and exported it to some sort of PC speaker format that I could read. The downside to this was it wasn't, when I'd preview it in Mod Plug Tracker, it didn't sound anything like it would sound in the PC speaker. So I had to fiddle with it, kind of figure out the value ranges and figure out exactly what to punch in to get it to sound right. But eventually I got that going and I was just able to hit the ground running. I think an actual audio guy who's composing audio and playing with Mod Plug Tracker every day could have modified Mod Plug Tracker to actually render the audio sounding like the PC speaker, but I didn't know how to do that, so my method worked just fine. So the reason why I'm talking about the sound immediately after video is because it's both tied together. They both rely on that interrupt timer that we just modified. So your notes are kind of determinant on the time slice that you choose, whether you sliced it up to tick off about 2 to 3 times a second or 2 to 3 times a frame or whatnot. So you need to lock this down early. Because if you were to, say, compose all of your audio and then decide later it's not playing back correctly because we need a more fine-grained interrupt tick, then you're going to be super inefficient because you don't want to slice that up super, super fine because then your game loop doesn't get all the CPU. So if you decide, hey, 2 to 3 ticks per frame is good enough, then you can compose all of your audio based on the fact that there are going to be a maximum 2 to 3 ticks per frame. So composing the audio is pretty simple, and then playing it is also very, very simple. You're really just outputting to 43 and then 42 with your note. So you can see that on the right, and then on the left is an example of just some of the code I wrote to decode the audio file that I had with the PC speaker data. So sound effects are one thing, but we definitely want music as well. And so one trick I did for the music was, even though we have one channel, I did that old trick of having 2 channels and alternating between the 2 really quickly. This isn't perfect, but it kind of has a neat effect and works for music. But unfortunately, to try and do that with sound effects and music just didn't sound right at all. And to do the effect where you're going to play music and then mute it every time a sound effect plays and resume it after, that also didn't sound right. So I made the ultimate decision to just limit the music to the title screen, main menu, and the mission stingers. And the rest of the game is just sound effects only. One huge advantage to using the PC speaker here, as you can see, is just how little memory it took up, and how even less memory it took up when it was compressed for the floppy disk. There are cases, of course, you can't do everything from DOSBox, so there are cases where you're going to have to test on real hardware. And the good thing is even your brand new quad-core machine can still run DOS. And it's super easy because you can just format a USB stick with FreeDOS, for example, and pop it in and you're good to go. And so I used this a lot. For example, the timing stuff and the sound stuff, it played right under DOSBox, but initially it didn't play right on the hardware, and I had to debug that a bit. But it couldn't have been easier. Just upload the build to the stick, pop the stick in the thing, which was tiny next to my keyboard, and test and just repeat. And it was a super great workflow. So keyboard input is pretty simple. So simple I'm not even going to cover it. But this game wouldn't have felt complete in my heart if I didn't support joysticks, and more specifically the Gravis gamepad. But unfortunately these things don't use USB, obviously, and they don't even use serial or parallel ports. They use this 15-pin port. And unfortunately for me, as I'm sure is the case for you, I didn't have any machines left with this port. I swore I did, but I went through all my old machines and none of them did, so I had to buy one off Amazon. But once it finally arrived, I was able to get going. And so when you look at this gamepad or joystick, you see these attributes. There's the x-axis, left or right. There's y, up and down, and you've got your buttons. So you would think that's pretty straightforward to read. You can just check a bit whether or not each button is pressed. And for buttons, you would be right. But for the x and y axis, it's a bit more complicated, as is the case with DOS. So this is some pseudocode to read the joystick position. So you output to port 201 just to say we want to read the joystick position. You create some variables, x and y, and set them to 0. And then you do a loop, reading port 201. If bit 0 is set, you increment the x variable, and if bit 1 is set, you increment y. And you loop until both of those bits are 0. And at the end of the day, you get a value, and that value is the position of the joystick. If that sounds super inefficient, it is, because depending on the machine, you might be looping 1,000 times, 2,000 times, 16,000 times just to get one frame of joystick input. So really not great. You would think maybe you could split that across multiple frames, but nope, it's timing dependent. In fact, it's so timing dependent that you want to disable interrupts when you're doing this just to make sure it's super precise. And joysticks being the way they were, you did need to calibrate them. This was actually kind of fun to do, and you can see here, for example, the center position for the joystick is approximately between 650 and towards 1100, and the complete range is towards 0 to 2000. Is anyone getting warm and fuzzy looking at this? Yeah, because I am. So in order to do it right, being distributed on floppy disk, I needed an installer. I wasn't satisfied just popping files on a disk and saying, copy it over. So I built my own installer. That's the time lapse. So it was pretty simple to write. I just created a packager which would zlib files. Oh, by the way, I'm Canadian, so I say Z a lot. And it would compress them that way into a little volume. And then the installer was pretty straightforward, a text mode thing that asks the user which directory to install to and so on. There was, of course, some DOS code that I needed to be putting in there that was specific, such as checking how much free space is available. But even in that case, like I do for the main game, I maintained a native Windows version. So everything I was writing for DOS, I would also write for Windows. I didn't go overboard. I didn't worry about the DOS character set, the ASCII graphics, or the colors. But that's only 1%, 5%, whatever percent of the actual development. So I was able to work on this, iterate, and debug it natively under Windows comfortably. One thing I did to decorate it was to have a little bit of ASCII art. Now, true ASCII art is amazing. You can use the entire DOS character set, and it is just mind-blowing, beautiful art. I went with the quick and lazy route, which was to just take a bitmap and convert it to one of 4 characters, the box characters in the ASCII character set. And then on top of that, I would RLE compress it so that when I render it, it would not only save RAM, but when I render it, I can just say, okay, spit out this character this many times, that character this many times. But finally, and it might seem needless at first, I also zlib compressed it. And the reason why is because this install.exe is stored raw on the floppy disk. And although you could use an executable packer, I wanted to be pure and just have it as it was. And I already had zlib in the executable to decompress the rest of the game files. So it was just one more way to keep that executable a tiny bit smaller. And so for those familiar with the game, you'll know that the engine is pretty versatile, and I ported it to all these platforms, including PSP and Nintendo DS, which were never released. But when it came to doing the DOS code, it started to get pretty unwieldy. It's pretty awesome that it works on all those other platforms, all the same code base in the same depot. But when it came to DOS, it was just getting too messy, and I honestly just didn't want to muck up my main code base. And so I decided to fork it. And this was absolutely the right decision. As cool as it would be to say, hey, I could modify the PS4 version today and click compile and the DOS version's updated. But, you know, you got to have some trade-offs. And this made it super, super easy now to just chop, chop, chop and get out the saw and cut it down for DOS without having to worry about maintaining those other platforms. Of course, the first step first, the easiest thing to do when you want to trim something down is to export your map file. So I exported the map file and converted the spaces to tabs so that I could load it up in Excel, sort the columns, and immediately I saw what the biggest bottlenecks were, which files were needlessly using way too much const data, which were using a lot of code, maybe that code could be cut down or cut out, and so on. So that's kind of a rocky montage because I think that anyone in this room, given a map file, you can kind of fill in the blanks and optimize your game. But once all the low-hanging fruit was kind of trimmed out, I had it down to 1.58 megabytes, which was awesome, but it wasn't a floppy disk. For a floppy disk, it needed to be 1.38 megabytes. So almost all of the work was actually chopping down those last 200 kilobytes, not chopping down the megabytes and megabytes that I originally chopped it down to. So one of the things, as programmers we're very familiar with, is generating data. Procedural generation's all the rage these days, and there are a lot of ways we can generate data. For one, at tool time, I would generate the pathfinding navigation data from the world collision data. So since I'm already storing the world collision data on the floppy disk, of course I don't need to store them both, so I just put the generation code into the installer. I also did this for car collision objects. So for various purposes, the cars have polygons, just line segment arrays, and bit masks. All those really need actually is a rectangle, a width and a height, and you're done. That gets rotated, and you can generate your polygons and your masks however you need. There was the caveat, though. is that I had to ensure 100% precise results. So I did have to do a bit of code, put a little stuff in integer instead of floating point, just to make sure that it was very consistent every time it was installed. The other thing that we've got here is compressing assets more. So of course I did zlib compress them to fit them on disk, but they still weren't crammed into a small amount enough of memory. So I explored all sorts of custom compression algorithms. So I looked at every single asset, whether it was text or sound or fonts, and I figured out, is there a better way to store this more efficiently? And so that was pretty fun, kind of just like looking at each asset byte by byte and just figuring out, can I RLE this? And it benefited two ways, because it could potentially use less space on disk, but it would also, and sometimes more importantly, use less space in RAM, because that was also something I had to fight for. Of course, when you're talking about two compression methods, like maybe I RLE compress these sprite graphics, but then I also zlib them for the disk, you will encounter cases where the original big uncompressed file passed into zlib will produce a smaller file than your custom compressed file that's super tight, but then when it gets zlibbed, it's larger than just the raw uncompressed, because it just can't be compressed as easily. So then you're back to that thing of code speed versus RAM usage versus disk storage. Which one is more important? Do I want to bump up the disk usage a bit in order to save RAM? And in many cases I did. So I did need to get out the buzzsaw as well and cut things down. So for example, the game being based in a city, a lot of the buildings, for example, had little details like store signs. And although they were kind of important for the core experience of the game, they weren't essential to the actual game itself or the gameplay. And so if you've got a bunch of art that's only used in one tiny part of the game, it's not really that important. And so cutting out all these kind of little details helped me really cut down the memory usage, because compression can only go so far. The other thing I did, which was simplifying the sidewalk. Specifically, I did this because other things will affect the amount of tiles you have. So shadows dropping from buildings, as you can see, those are going to be baked down and generate unique tiles, as will debris or litter or anything else that's over top of the sidewalk. It all gets flattened, baked down, and sliced up into tiles. And so if you have multiple different sidewalk tiles, then the same shadow here and the same shadow there will actually generate different sets of tiles, even though it shouldn't. And so when you use just the same tile, you'll use less tiles. Another thing that I had in the game was the background art was split into two different banks. So if you're on this side of the city versus that side of the city, I would be swapping one in and the other one out. But the reality is that both sides of the city have roads, both sides of the city have sidewalk, grass, trees, and so on. So there was a lot of wasted space there. So by sorting it and combining all of the duplicate tiles into their own separate bank that was fixed in memory and only swapping in and out the unique tiles, that's of course an easy win. But while we're at it, now that we're swapping stuff in and out of memory, what else could we do that? Well, the main menu and the pause menu, the game world's never being displayed when those are active, and the same could be said for cutscenes. So I could swap them all in and out of the same memory slot. And the one thing I'll mention, of course, is that the size of that slot is exactly the largest size of one of these four. So you're making sure not to waste any memory. The cool thing is that it doesn't matter if you're running on an XT or a 286, the slowest PC around, your hard drive is still relatively fast, especially when we're talking about a few hundred kilobytes here or there. So even if you're loading in and out a bunch of data when they go to the pause screen, it's a split second, it's irrelevant. It's not like the floppy disks were just grinding away while you waited. So that gave good space savings, of course, but we still did need to worry about performance because a huge amount of our frame was drawing this background. And so if you look at this, you'll see there are a few things that you'll notice. Number one, because it's based in a city, there's a lot of sidewalk and a lot of road. And number two, the road is mostly a solid color. So I think you know where I'm going with this. So continuing the strategy of sorting tiles, I sorted the solid colors to be the first four and the sidewalk to be the next two, and just drew those in code without actually fetching the pixel data. And that was a huge speed increase. So the game itself also did have a DS port, although it was never finished or released. And this was cool because the DS actually had native tile-based graphics hardware. So the most exciting part here was how the game does screen effects where the screen waves with a sine wave, and it does the H-blank. So on each scan line, it adjusts the scroll to give a nice sine wave. And of course, on all the other platforms, I do this in software, simulating what the real thing would do. But when I ported to DS, I could actually use the real DS hardware to adjust the scan line and get that effect with no CPU overhead, which was amazing. All of you, I'm sure, are familiar with how tile-based graphics work. If you're not, you can just pop up on YouTube. I've got this video as well, which goes into more detail about how the graphics were made and how the sound was composed. But there's one thing that I'm going to go into, which is the game itself and why it is what it is. So it was designed to be like an NES game, and although by the time it was ultimately finished, I did bend the limitations and restrictions a bunch, the core of it was based on the NES, and more specifically, NES games with the MMC5 chip in them. So every single NES game from 1986 onward about had some sort of chip in the cartridge. And I think everyone's familiar with the Super FX chip, which Star Fox had on the Super Nintendo. But every single NES game had some sort of chip, not nearly a fraction as powerful as that, but they had some kind of chip which would extend the hardware's capabilities. And so on a standard game console, you would see is that simple single ROM chip, which contains your program code and data and graphics, and it goes through the single bus to talk to the CPU. But on the NES, you had two separate buses and two separate chips. Now, why is that important? Well, here in this case, on pretty much any console you can name under the sun that uses cartridges, you've got your program ROM. It talks to the CPU over the bus, and whether you're writing to ports or registers or whatever, your code will then talk to the CPU or the GPU and do the graphics and all that. But on the NES, you had two separate chips. One was dedicated to the code and data, one was dedicated to the graphics, and that was hardwired directly into the GPU. So when your screen was being drawn, from top to bottom, left to right, pixel by pixel, in real time, the GPU was fetching the next byte from the ROM to get the pixels to be displayed. And this is really, really, really cool, because you had direct access to that, so you could, and as they did, put the MMC5 chip or any other chip between that and hijack it. So when the GPU wants to read the next tile, you can do whatever the heck you want. You can automatically bank switch based on the address it's reading. You can do anything. In fact, a project that I wanted to do that I never got around to was you could probably build some sort of device that would hook up a modern console to an NES through the cartridge and feed the video, do video capture so that you're actually displaying the video capture from a modern console on an NES through this because you have direct GPU access. But in any case, the long story short, on a stock NES, you could only have 256 background tiles at once. With the MMC5 chip, you could have 16,000. So that's a huge difference. And the reason why I mentioned the DS specifically was because 16,000 background tiles is actually a lot, even by DS standards. But the DS had other capabilities which I could leverage. For one, the NES was just a single background layer. But on any other console, pretty much, you had multiple background layers. So back to sorting, I sorted the most commonly used tiles to be fixed in memory and used them in one tile bank and on one layer. And then the rest I would just stream in dynamically as they were needed to a second layer. And therefore, I got my 16,000 tiles. And I used little CPU overhead because most of the time you were just rendering the common tiles. Another trick I used, which I'm pretty proud of, is a palette trick. So the tiles in RCR were 2 bits per pixel. But on the DS, you could only do 4 bits per pixel or higher. So you would be wasting space. You would be, but you don't have to be. So if you were to, say, store 2 2-bit tiles in a 4-bit tile slot, and then take its 2-bit palette and make 2 separate 16-color palettes, you can actually switch between which one is displayed by switching which palette you use. And so tricks like that were pretty fun. And I used to work at Digital Eclipse on all sorts of stuff, like emulating arcade games on PSP and stuff. And those days were just so fun, because every day was figuring out stuff like this. One of the coolest things was when we were doing Mortal Kombat on PSP, emulating that. And I profiled the ROM emulator to figure out where the bottlenecks were. And then I disassembled and rewrote key routines like drawing the shadows, which was originally drawn in the emulator code, which means that you're just like churning away at the emulator to draw these pixels of the shadow. So instead, I would rewrite that in native C code, and then the emulator would hop over to the C code, run that, draw the shadows really efficiently, and then hop back into the emulator and keep emulating instructions. So every day was a fun challenge, and I really enjoyed that stuff. So I'm a big proponent of automated testing. And so here you can see, even running on a Pentium 1, I have the game running at super speed, testing itself. And the way I do that is by recording the button input, ensuring that my game engine is deterministic, and just playing it back. And I did a talk on that last year, which is on the Vault if you're interested. But the cool thing about this is that not only can I automatically test the game without actually having to do the manual QA myself, but it has a lot of other purposes too. So for example, every game engine, we're going to have random buffers here, pools there. We might say, okay, we need entities in our game. Let's just create 100 slots for 100 entities, because 100 seems like a good magic number. But when memory's at a premium, we really don't want to deal with magic numbers. We want to deal with certainties. And so one use I had for these automated playthroughs was to hook up some sort of log. So I logged just how much memory I was using in these pools, the most allocation I was doing, and how many slots I was using, and all of that. And after the game had played through hours and hours and hours of itself, over and over and over again, I had a pretty good idea of exactly how much to trim these buffers. And it was a huge space savings. And if I didn't have all of these hours and hours of playthroughs that could run at super speed, I'd maybe have to guess or whatever, but now it's pretty certain that these are trimmed down to the right amounts. The other thing, of course, is I did have to cut some content. The entire story mode pretty much is in there, so it's pretty much the entire game. But there were certain extra characters, like Super Meat Boy was playable, and Commander Video from the Bit Trip series. Those had entirely unique character sets of all the animations and stuff, so that was really taking up RAM and storage space, so I had to cut those. Mini games as well. And there were some pseudo 3D racing sections, and so those could have, they were not only a bit of a CPU hog, but not the end of the world, but they also had really big sprites, which were taking up a lot of graphics RAM as well. And finally, the localizations. Although the original game was eFigs, English, French, Italian, Spanish, German, the game itself uses about 23,000 words, which is a lot. And all localizations combined, uncompressed, were about 950 kilobytes, which is also a lot. And so I could have, of course, cut that up and paged in and paged out the localizations from the hard drive. But that still kind of didn't save me from the floppy disk and trying to get it down to 1.44 megs. So I made it English only, unfortunately. Another thing I did was in RCR, I got a bit carried away having tons and tons of different fonts in the game. And so a lot of these were redundant. You have a bunch of fonts that are about the same size. You don't need them all. So I went with the simplest approach possible, was to just add this ability to reroute different handles to the same font definition. There was some work to go in there and just adjust things, because maybe the font was a bit wider or so on, but it wasn't too bad, and it saved me from having to actually modify all of the data and all the attributes on all the text in the game and whatever. They still use the same original font handles, but they just displayed a different font now. And this is the side effect of why the text bubbles are now black instead of white. I could have had some code to invert the text or whatever, but I just figured keep it simple and just use a single font. I, of course, did have to use a DOS extender, because even though every PC 386 onward was a 32-bit machine, DOS was 16-bit, and that's just how it was. So in order to take full advantage of the 32-bit architecture and have memory in a somewhat linear fashion that's easy to access, I had to use an extender. Whatcom amazing, 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 made that easy, had them all built in. I could switch between them and compare, and ultimately I chose to use P mode because that used the smallest footprint and entirely embedded in the executable. There was no separate runtime needed. Yeah, so I'm sure most of you are familiar with this, that DOS had the 64K of base memory. And if you're using malloc, you're not getting that. And so if you're trying to, when you're talking about things like in the range of 4 megabytes, 640 kilobytes is a huge portion of your memory. And so in order to access that, I wrote a little custom allocator, which uses the DOS memory allocation. For more information on that, you can check out this link above. The slides will be online as well later. But that was a great website that gave me the resources I needed to get this going and access all of the memory. I wrote a simple allocator that would just automatically allocate from either the bottom 640K or the rest. But I could also manually specify which area I wanted if I wanted. A common question I get asked a lot is, did you write it in assembly language? How much assembly language did you write? And although the DOS version was written, or the NES version was written in assembly language, that was an entirely separate code base and it wasn't the full game, it was just a prototype. For DOS, it's almost entirely written in C++. And I'm a huge proponent in high-level languages because an algorithm is often superior to assembly language. If you take some code and you decide, this isn't very efficient, I'm going to rewrite it in assembly language, you may take it from here and squash it to here. But you're just kind of squashing it. But if you think about it differently and you really need a performance gain, often what you really want to do is think outside the box and think, is there a better algorithm I could use? And that's kind of that's not DOS specific at all. That's just a general programming tip that you should always be thinking about. Is often there's some algorithm out there that's better than just kind of optimizing your code, so to speak. But the one trick that I like to use is to finesse the C to produce better instructions. So you work hand in hand with your compiler. So a lot of compilers are awesome enough to have this option to compile and convert your C to disassembly. If they don't, you can still do this. Just set a breakpoint, run the debugger, and once the breakpoint's hit, switch to disassembly view, and you can also see what code was generated. So in this case, for example, you can see two equal functions that do the same thing, but one generates much tighter code. So if you were to do this on the left, you're going to generate better code than on the right without actually writing any assembly language yourself. And this can vary depending on the architecture. So on some systems, the one on the right would actually generate tighter code. So it is good to be aware of the architecture, but if you're lazy, you can just do trial and error and back and forth check out the disassembly you're generating. So one thing with RCR was that it did use floating point, and that is a bit of a troublesome problem for old PCs. If I were to write it from scratch and wanted to target a 286, I wouldn't even use fixed point. I would just say, hey, look, the bottom 4 bits are the subpixel, the top are the actual pixel, and I just shift right 4 times and I get my pixel position done and done. Don't worry about exponents, no floating point, it's easy. But unfortunately, my codebase did use floating point. And so compilers will have floating point emulators, which you can use. And also, from the DS version I had originally written, I also had a class that I wrote that would do fixed point automatically for me from my floating point. But neither of those is really ideal. They're going to be inefficient because, like I said, I don't need full floating point. I just need some bits for the subpixel and the actual pixel position. Ultimately, I decided that this was kind of slowing down the game and I didn't want to do it. And so I made the floating point coprocessor mandatory. Every single PC from a 486DX onward would have the coprocessor. So that was kind of culling a bunch of PCs before that. But it was a compromise I decided to make. And the game will actually run on a 386 if you do have a coprocessor, the x87, but most didn't. Another kind of hack I took was to give better AI with more RAM. So I detect the amount of RAM available, and if less than 4 megs is available, I just do dumb AI, and if more is available, then I actually load that fat pathfinding data that I generated from in the installation. So, not ideal, you know. This means that if you only have 4 megs of RAM, you're not getting the best game experience possible. But the reality is that most of the time it's not pathfinding anyways, and it's still fully playable. Another thing that I did here was give the frame rate option. So the game can run at 60, 30, 20, or 15 frames a second. On a Pentium, it runs perfectly fine at 60, and on a 486, it should be great at 30. But you might ask yourself, 15, that's insane. But if you actually boot up your old DOS games, you'll realize that a lot of them actually ran at 15 or even 12 frames a second. So 30 or 60 is pretty good. Another thing I did was the Windows 3.1 prototype. So this was fun because I already had my Windows build, of course, so it was just a matter of compiling this in Whatcom. DirectX didn't exist back then, though. And so there was a big reason why even when Windows was massively adopted and we were all using it, we were still kicking back to DOS to play games. And that was because GDI was super, super, super slow. And one of the crappy things about it was that everything was drawn upside down due to their decision to use that coordinate system even for bitmaps. And it wasn't until Windows 95 that you could actually just feed in a negative height and be done with it and good to go. So everything was drawn upside down. So it was already super slow and inefficient. Gotta say that. But it was even more inefficient because in this case, I would either have to draw every single thing upside down, so I'd have to rework my whole renderer to draw the fonts, the shapes, the background tiles, the sprites, everything upside down, or you have to have a pass before you render each frame to manually just flip line by line through some mem copies, and that's not good either. So it's kind of a lose-lose scenario unless you want to put in the work. And the other thing is there's no trivial way to do a consistent frame rate. So you've got your WM timer, but that's not very precise. You're not going to get that ticking at 60 hertz. And on top of that, it's completely unreliable. Even if you set it to be at whatever rate, it'll be that rate plus or minus some value. So Windows wasn't really truly an awesome games platform until DirectX and Windows 95. One thing I want to say is just as someone who's ported the game to so many platforms, you can really benefit a lot from that. And it's not just about taking the game, getting it up and running, and shipping it. I tweak and tune each of the ports to play best on each platform, and you learn that. And so there are benefits, of course, performance and memory usage. So when I originally ported it to 3DS, I'd crunched the game down, and that kind of was what gave me the light bulb. Wow, I've gotten it down to only use 54 megs of RAM. Maybe I could get it running on DOS. And then I crunched it down to the 4 megs for DOS. But after that, I had found all of these performance things that I could optimize. And so I ended up backporting that code from DOS to the main engine, a bunch of it, and then pushing out a 3DS update so that the 3DS version would run even better. And when it comes to my new game now, my 3DS engine is even more efficient now thanks to the stuff I caught with the DOS port, and now I can push even more pixels. And I was also tinkering and playing around with the PSP version again. I originally had done a PSP port back in 2009, shelved it, and I dug it up again recently and started playing with it for fun. And even though, unfortunately, I heard the news that they're shutting down the PSP store, so I guess it'll never come out, it was still very useful because I optimized the sound code to have a smaller footprint and be more efficient for PSP, and I was able to bring that back into the mainline engine for the new game coming out as well. But it's not just about performance. So I recently ported the game to iOS as well, and I wanted it to play as well as possible on the touchscreen. So I did a bunch of code there just for gameplay, where if the user is aiming to shoot an enemy, it does a bunch under the hood to make them feel like they're a really, really good shot, just to compensate for the touchscreen. And when I looked at code like that, I was like, you know what? Why does that have to be on the touchscreen version only? I could bring that to the console, and even if they're playing with a controller, it'll improve the gameplay experience that much more. And so with each port I do, I'm able to find things to tweak and tune the game to be better, both performance-wise and gameplay-wise. So how this all started, how I did a DOS version, well, I wanted to do a DOS version since long before Retro City Rampage even came out. And I started tinkering around with it and realized how much work it would be and decided I had to shelve it. And the reason why Retro City Rampage has those video filters where you can switch between a pseudo EGA mode, CGA mode, and all that was actually for me personally because I figured, well, if I'm not going to do a real DOS version, at least I can have the option to play this game in an EGA or CGA mode. But, you know, the thing is that before I went into game development and this was my career, I was a hobbyist. And I was always tinkering around. And it was so fun. I was just in a toy box just using code like my Lego blocks and just playing around. But once I started working in the industry for other studios, and then once I started my own game company, it was just all about milestones, shipping, how commercially viable is this, and so on. And I stopped playing. And so being go, I went straight from RCR, even though my next game is not even out yet. Oh yes, right after RCR, I was updating it, I was doing ports, I was doing prototypes for new games. I just hadn't stopped. And so eventually I kind of hit a wall. I was working on prototypes for a new game, and I just wasn't feeling it. And I was feeling a bit burnt out, and I decided, you know what, I'm going to take some time off for the first time in a long time. I never really take vacations. Of course, that time off turned into me porting the game to DOS, but honestly, it was more rejuvenating than a beach anyways. Porting to DOS really, I went through a bunch of stuff here just talking about how DOS worked and crunching some memory down. But at the end of the day, it was actually more interesting than I think my talk gives it credit for. It really was to me like a Sudoku puzzle, like playing Tetris. And every piece of it was just the most invigorating, fun time I've had coding in years and years and years. And once I was done, not only was I super ecstatic that I had this DOS version that fit on a floppy, but I was so invigorated that I was ready to hit the ground running and get back to the new game. So for more information on this DOS port, I actually did an interview with Gamasutra, and I talk at a bit more of a high-level perspective, a bit less technical. And for the NES version, how I did that and how I wrote that in assembly language and all of that, I have a video on YouTube called The Making of ROM City Rampage. And that is it. So I'm here for any questions. Yes, thanks for coming. Hi, yes?
Hey there. Thanks for a lovely talk. I maintain an open source engine for 2D games. And when I talk to other programmers, and one of the features is that depending on the target platform, it only adds about 200 kilobytes of like binary code. And when I talk to other programmers, I often get the response, I don't care about that. And like, besides probably from all these awesome people here, like, why do you think programmers these days like don't care about that, even though I think it's still very much important?
Well, it's interesting because when I started making games, first I was a kid and I said, I want to make games. How do I make games? And luckily my sister's boyfriend happened to know how to do some programming because of his high school class. And he's like, oh, I use this thing called C++. And so I said, that's great. And so I learned C++, and that was how I started. Nowadays, when people are like, I want to make games, how do I do it? People point them to Game Maker or Unity with C# or whatever, and that's all great, but it just means that they're starting at a higher level and not necessarily getting the foundation of it. And also there's the old thing of computers just keep getting faster, so whatever, right? But me, I'm a bit of a neat freak. I'm actually more of a neat freak with my code than I am with my kitchen. So I just like keeping things tight, even if sometimes it's a waste of time to be spending that extra effort.
Well, thanks for the talk, and I hope it inspires other people.
Oh, thank you very much. I'd love to see more DOS games. Yeah. Any other questions? Don't be shy. Good. All right, well, thanks again, everyone, for coming. We're right at the 60-minute mark, so perfect timing.